So great to see you, Man of Stone. Okay, for everybody, my name's David Stanley. I host the Spiritual Journey on YouTube. And tonight we will be looking at part two of Flat Earth. Yes, this is part two, Flat Earth versus Globe Experiment and an update. Hopefully, Man of Stone will be able to fill us in on what is happening in the Flat Earth experiment world. So, over to you, Man of Stone.
Well, what would you like to know first?
Well, if you'd like to give a short presentation, that would be great, and I can ask some questions as necessary.
Sure. Okay, well then I might as well just share my screen here.
Yeah.
Sharing is not turned on, so you have to turn that on first.
Okay, so where do I find that?
This is your interface, not mine.
There's nothing showing at the moment.
Well, let me just hit this send request, see if that helps.
Oh yeah, I've got it.
There we go.
Right.
Multiple sharing is now on. That's very good. Okay, so then, yes, now I get to pick. Okay, so let's start with a picture. And that's this one here. These are just a couple of pics that are from some of the historical videos that I've produced on the subject. The experiment has to do with what's going on inside a standard airplane or jet these days in regard to the system people use when they're approaching the runway and attempting to land. There is an array, which is exactly what we're seeing in this picture here. It's called an ILS. It's called an Instrument Landing Service. And this particular component of it deals with the vertical vector that the pilot is flying in terms of what his rate of change in altitude is in approach to the runway. This is merely vertical feedback relative to the actual spot on the runway where this array is planted typically. This ILS is a pair of emitters actually. Two EMF signals are being sent out upward. Actually, one is sent directly level. So let me show you the angles at which these are being sent, and that is it here. You can see that from, this is left to right, but here we have one emitter on the array on the tower, and this is the other tower emitter here, where one of them is focused to fire out a beam level with the runway, and one of them focuses a beam that is upwards at 6 degrees outward from the runway, upward toward the craft. So the craft has two receivers individually tuned to these particular frequencies, and it makes a comparative through the electronics in the dashboard, a comparative signal strength comparison here, so that if it perceives that this signal is coming in as strongly as that signal, then we are coming down the middle at 3 degrees, which is exactly the half between 0 and 6 degrees. So let's see, we'll change what I'm sharing here just for a second, and we'll go over what I present in a 2-pager, in a PDF here, and it's at the top. And we're going to be using that ILS system exactly in the scenario as you see it here in the picture in figure 1. What I'm circling right now is CYVR, that is Vancouver's International Airport in Vancouver, BC in Canada. And off one end of the runway out here, this point right here is 20 nautical miles away from touchdown point on the runway, from the beginning of the runway. Up here, this is the direction that ILS pair are firing their signals in this direction here. And a plane on this part of it, on the approach leg, will be intercepting those signals at 20 nautical miles away, right at this particular point here, where it is a particular distance, vertically speaking, above the runway height. And when we look at the math, it comes to this figure here, which is, let me see, I'm going to select text, 6,355 feet above the runway altitude. That is going to be a standard, simple measurement of horizontal, straight across looking at this. So what we're looking at is an approach where here's the plane approaching the runway, but in terms of this experiment, the plane will be flying level. He's going to use his altimeter on board, which is a barometric instrument, and it is calibrated using a figure given by air traffic controllers who live on this runway, and in advance publish exactly what the barometric pressure is at the runway at this altitude here. We plug that figure into the altimeter on board the craft, and it is calibrated and can tell you using simple pressure change over altitude. That's how an altimeter works. That's how it works in every aircraft. And it has to be necessarily precise because lives are on the line here. So everything about this technology is necessarily as precise as possible. And the signal we're getting from this tower, of course, is light-based. So the indicator of where you are on this line is almost instantaneously transmitted to the craft, moment to moment. So this rests on, like I say here, on the pilot's ability to maintain the proper altitude, as in his ability to fly level and straight and say at 100 knots. And this is what we would easily be able to do with a Cessna, which have a typical cruising speed of about 115 knots. So this fits well within the capability of any standard small pleasure craft, single prop, cheap to rent, cheap to own, cheap to operate. This is what we're going to be doing. We're going to have the plane flying at 6355 above the runway altitude, and whatever the altitude that the runway is above the ocean is just simply a coefficient that you subtract at the top of the equation. I should mention also immediately, the first priority here is that we're picking a path which is necessarily over the water, because as we all know, water's flat, and it also will give you the least amount of variability in what your barometrically tuned altimeter is going to tell you about your altitude moment to moment, that there is the least amount of distortion out here over the water. There is no, land type or aspect or sun angle to be considering here, which is why we have chosen this particular format for the method. Okay, so in case A, which is what we're looking at here, where the Earth is flat in this scenario, and we're 10 feet over the water at this altitude in Vancouver, so we're ignoring that, and we're just dealing with the 6355 figure here, that when the plane is approaching the ILS, when the plane is approaching the runway, flying this pattern here, when he is just still working his way towards the 20-mile mark away from the airport, his glide slope indicator will be telling him when he's about to approach this exact point in space. And when he does, you take a measurement and you confirm digitally that your distance to the tower is indeed 20 nautical miles. However, if the Earth is convex, then we're looking at this other solution here, where because the Earth is dropping away as we come away from the airport in our approach, that at 6355 above a surface that is dropping at 8 inches per mile squared away, you will actually not intercept this 3-degree slope until you are 18.9 nautical miles away, not 20. Now, when you're flying a Cessna and you're doing about 100 knots, which is entirely reasonable. The time difference between the two measurements that you can expect will be about 39 seconds between when you are 20 nautical miles away and when you are 18.9 nautical miles away. There are 39 seconds that are going to go by. Regardless of the shape of the Earth, it's just a matter of we're going to take a reading at this moment, or we're going to take a reading at this moment. And those two moments, when flying level at 8 inches per mile squared, happen 39 seconds apart from each other because the distance between them is some 353 feet, flat to curved. So this is the reason that we've put this method together. So as a matter of what else I would want to show you, just to clarify everything that I've been talking about, let's get over to a couple of frames of the part 2 of a 2-part video that I put together in reaction to some things that Eric Dubé said, some things that Derek Marbles said. And the 2-parter video is really my reaction to correcting the things that they've said and providing a better way to verify the things that they're saying than the methods that they originally propose. So if I were to show you what this looks like in terms of the chart itself, I would take you to frame 110. Here is one here. Oh no, let's go right back to the PFD, number 69, which is right about here. This is what the pilot is looking at in his primary flight display. Now, the purple, of course, we could ignore pretty much. That will say 100 right here. Of course, he'll be doing 100 knots when we're taking our measurement. The pink is the glide slope that we're talking about, and the indicator is here. The pink diamond slides up and down past these dots below and above to tell you when you are below and above that 3-degree slope as you approach it. The purple, again, speed, this is horizontal speed, and this is vertical speed in terms of feet per minute next to it, to the right of everything outside of the green. The QNH, in this case, is referring to the barometric pressure setting that I was telling you about, how on the runway, air traffic control will give you a slightly different figure than this. The QNH figure is for people in jets flying at 13,000 feet, and there is a standardized assumption about the pressure at 13,000 feet, and that people are working across that standardization when we're stacking planes 100 or 500 feet apart as they fly past each other through the air, and the air traffic controllers are setting all that up. The orange here is the localizer. This is the horizontal or the azimuth equivalent of what's going on with the glide scope. There is another beacon down on the runway sending him to his craft an indication of, is he approaching the runway on the correct heading, and we're using none of that in this analysis. Down on the lower left, the blue, that is the name of the ILS tower, that they all have distinct frequencies. This one is 108.7, but the 7.4 nautical mile measurement here is, again, directly what you're getting from that EMF emission coming straight to the craft from the runway, and telling you exactly to the 10th of a mile here how far away from touchdown the craft is at any given moment. So that's really what's going on there. If we're going to be looking at the charts, let's start at figure 110. Right about there. This is one chart, and I've simplified it. There are actually a lot of other distractions in all the rest of these boxes when you look at a standard airport chart printed by Jepson or printed by anybody else out there who makes airport charts. What we're seeing here is the runway at 8 feet above the ocean. The runway's title is 22 left, as you would approach it at 220 degrees azimuth, and you would hit, it's a pair of runways, and you're choosing the one on the left to land on. But what's important in here is the point at which they typically have incoming traffic intercept the glide slope to begin with, just generally. It happens at 1500 rather, to 2,000 feet above the runway. This is the point at which you fly in at whatever angle, at whatever heading, and you eventually bring your jet or plane about to 219 degrees as a heading, and then you intercept it at precisely 5.0 miles away from the runway, and you descend at 3.00 degrees. And I like that they're using 2 decimal points in saying that this is exactly 3 degrees coming away up from the runway towards the craft. That is the way it looks on this chart. Here's another chart where it's left to right instead of right to left. Again, glide slope at 3 degrees, intercepting at 6.1 miles away from the runway at just under 2,000 feet above the runway itself, 1929 or something, whatever that's going to come to. And again, this is very typical. Another typical one here, flying in the other direction, just like the first one we saw, where again, 3 degrees is the angle coming from those towers. We're intercepting at 2,000 feet, minus 33, above the runway, at 6.0 miles away from the runway. So what I did in these particular, the 2-parter video here, previously, a couple of years ago, was I was attempting to get this same kind of data 10 miles away rather, from the runway. I would actually have planes or pilots take their commercial jets and approach the runway up here at a much farther distance away, closer to 4,000 feet up in the air. And they would intercept this same 3-degree angle at 10 miles away. So I have a series of data from a couple of pilots, one of which who trains other commercial pilots, and I have video recordings where they take their phone, they sit it down on the console, and it is literally videoing that first screen I showed you of the primary flight display. And I have, plotted all of these out and produced the 2-part video, which I recommend everybody watch. It's very enlightening stuff. So when we take that far, that's the one I first showed you. So we'll go to 139. This is one of the airports in the video. Actually, it's Hanoi in Vietnam. You can see up in top right, and it's a very busy chart. As you can see, what we were looking at before is nested right in here, right down to the indication of 3 degrees on the chart here, unedited, just so everybody can see it. 139 and 140. There I am simplifying the chart again. And you can see how it's situated over land. But in this case, all of this is essentially at 0. It's marshland. It's the same height as the oceanic water, which is just a little bit to the south of Hanoi. An esoteric point. But I invite everybody to watch those videos and see how this came about. What we're doing in the method for this particular experiment, we're taking it right out to 20 miles instead of 10 miles. It's really the only difference. And I think it's probably a better way to go at 20 miles away, because the difference between here, like I said, was 353 feet between these 2 scenarios. At 10 miles, it's closer to somewhere between 100 and 120 feet. I don't remember the exact figure, but I'm sure you get the idea with the trigonometric function here. Anybody can work that out. It's half. So that's the long and the short of this method, that we're taking a direct reading, flying level, approaching a 3-degree light source, and our equipment that is on and is the same in every aircraft tells you exactly when the moment is and the distance from the tower when you intercept this 3-degree line. I hope that's clear.
I think
that's the recap.
How many years have you been working on that?
Nearly 4.
Nearly 4. Wow.
Yeah. It's been quite the trip.
You've collected a lot of data. Yeah. And originally the idea came from Eric today, I believe.
Well, yes, Eric wrote a kid's storybook where there's this child and he hangs around his grandpa, and grandpa's always telling him about the world and about science and particularly about flying. And in the story, grandpa takes the kid up in the plane and says things like, okay, and I'm sure you've all heard it, that when you're flying around something round, you know what I mean? And I can actually share that picture too. Let me get back to my sharing this frame here, and we'll go right back to the beginning. And I'll show you the one that I mean. The picture that he put in his video that I lifted and put into my video. It's way back at the beginning. Here we are. And there it is. This is the crux of part one, and the reason that I produced that video to begin with. And it's all about how the grandpa tells the kid that, if I just fly level, I'm going to fly off the edge of the earth. I'm going to go out in space here if I don't dip my nose when I'm going over the surface of the earth. Because, every 30 minutes it's this many degrees and yada yada at 100 knots and sure. But that led to the other part of the reason I put part one together, and that's what Derek Marbles then did in response. And it was to take a spirit level, a torpedo level, on board a jet with him, and he sat it on his tray in the craft and took a video of his phone, which has a level function on it, showing level on his tray and that it's not changing while they're flying. Well, the problem is that that's a moving reference, that as the craft continues to move, so does vertical in the Globee model. That vertical is now this way. If this craft moved over here and is now over this part of the land, the level has also changed angle with the land, with the craft, with the land, and vertical is now this way in perspective of the people in regard to the reference frame of those in the craft, that this is now vertical for the people in the craft. And of course, the level is not going to show any change going over this angle because everything else about the reference has also changed. It's called a moving reference. And that's why I put part one together, mostly, was to just poke fun at these guys for the totally poorly thought out assertions that they were making at the time. And so that's really the impetus behind what we're doing here. And it's one thing to make fun of other people, but while you're doing it, if you're shooting their ideas down, personally, I like to have a policy that I want to have the better idea that I can just whip out of my pocket and say, no, not like that, like this. And this is really the purpose of those two videos. I mean, when you watch them, I come off like a big meanie every once in a while. But frankly, that is the kind of feedback these people need, that everybody in the flat earth community needs when they say things that are not really as well thought out as they could be, that are not really helping the flat earth community because they're saying things that globies can easily tear apart and make you look foolish and, of course, blow your credibility out of the water. So I'm kind of helping and hurting the flat earth community at the same time, if that makes any sense.
I've got to say thank you at this point because you pointed that out to me about 2 years ago. We were in contact, I think it was on Miss Witt's group, and you pointed this out and you said, spread the word, will you? Because I understand
Yes.
the concept, yeah? So, yeah, that was spot on. Now, we don't have much time left. You've done a wonderful introduction there. Now, this whole video, this whole experiment has been sent to Shiva in America, yes, for him to look at and for his scientists to look at. And they can then get together with flat earthers and find out if it's true or not. Yes, find out if there's any curve or if there isn't any curve, and it will all be scientifically done and tested. And according to Shiva, this should end the debate, really, because if there's no curve, then Earth is flat. Yes.
Right.
So I'm really looking forward to what Shiva and his team will say. Now, in his video, which I will post under this video, he said that we could start this about the 13th or the 14th of June. So
Can't wait.
yeah, but then comes up the question: if that does happen, will you yourself be able to fly out to America to oversee this experiment?
Well, probably not, because I live in Uruguay, and that's rather a long flight. And it's not just the cost. These days, it's also about the DEI lottery in the sky. That I don't want to die that badly. I think this is the kind of experiment that can be so articulately defined and described, and the method can be so simplistically laid out that it's really hard to screw it up.
Yeah.
That I don't think I need to be in the plane. All I really need to see are the videos. And it's one thing that Dave Weiss asked us when I was presenting it to you guys last week. You remember, he said, okay, Stone, that's all very and good. This is a really good thing. It looks good. I like it. But can they fake it? Was his question. And I'm thinking no, you probably can't, because the same phone recording being used to record the primary flight display can begin by simply lifting the phone, looking out the front of the cockpit, and seeing the runway 20 miles away. Okay. On a clear day anyway, and then bringing it back down and taking the measurement and looking literally at the flight display when it says 20.0 in the bottom left corner, and it's got the correct ILS address for that tower in the lower left, and the glide scope, the little pink diamond comes down and hits right on the line as we see it go to 21 to 20. When all that happens simultaneously, that's pretty hard to fake.
Yeah, you said that in your consideration that this experiment is foolproof. Yeah, pretty
much. And I think it's good because we can give it to the flat earthers who are going to do the same thing. Yeah. Allegedly objectively, as the Globies might do. And again, their video will show the PFD, it'll show the airport, and here and here and here, and here's how fast we're going. And if the Globies post one where it's only 18.9, and then the Flat Earthers post one where it's 20.0, I think we know what's going on here. That'll be the ultimate indictment.
Yeah, and this can be done all over the world. With flat earthers and globers that own a small aircraft,
or can rent, because you can rent a vintage Cessna for as little as $150 an hour wet. All you need is your own certification.
I never did complete my pilot training course, but I did fly in a Cessna at one time, and
cool.
We did a loop-the-loop. Yes, that was pretty cool, I'll tell you. That was with the RAF.
I bet it was. With the
RAF, and I didn't have a choice. He said, we're doing it. And I said, right, okay. So, yeah. And the only thing I really learned on my pilot training course was to land. He said that was a perfect landing.
Cool.
That's good enough. That's good enough for me. So I don't really need to continue with this.
It's that final moment of sheer terror just before the wheels hit the ground, isn't it? It's that one where, I've been dropping at 700 feet per minute for quite a while now, but I better slow that part down.
I didn't really have time to think about it. Right.
Yeah, no doubt.
Okay, so thank you very much for your time.
Surely.
What time is it there now in Uruguay?
It's 3:30 in the afternoon.
Okay, so it's 7:30 here,
Right on.
7:34 um, in the UK, London time. Thank you very much for your expo. Can I put the links that you gave me under this video in the description box? So that
Yeah, I
people
would
can have a look.
recommend we handled that question one time, but just to be clear, like I would recommend posting the Dropbox links for the PDF that I showed you,
Yeah.
and if you want to, the interview or the presentation day last week with Dave, or not, but post the two BitChute links to my videos, to
Okay.
the Dubai part, the part one, part two. Yeah,
Okay.
post the BitChute links for that, and then people will know where to find it and how long they've actually been online, and how long this has been going on.
Okay. So I can say thank you very much. Yes. Um, I hope this will help a lot of Globers see the reality of the flat Earth, or if the scientists tell us that really there is curvature there, we'll have to consider that as well.
It is my absolute pleasure. And as far as the Globies go, the first thing I'm looking for in their reactions are, of course, objections.
Yeah.
And what those could possibly be. That, I think, is going to be proving to be most entertaining about all of this, beyond the victory itself.
Well, to every thesis, there's an antithesis.
There
Um,
is.
is that flat earthers normally see through um, any badly formed um, antithesis. Yes. So once again, thank you and good night.
Very good.
And um, I shall now get this loaded up onto YouTube.
All right, let's make her go. All right, talk to you
Okay.
soon.
Thank you very much, Man of Stone. Oh, can I have your first name? What's your first name?
Oh, everybody calls me Stone. Even my wife calls me Stone.
That's good enough. Stone.
Yeah.
Okay. Okay. Well, I was thinking there's a lot of sharp Glovers out there, and they are sharp as scissors. Yes. Okay. So
Looking good.
on that note, we'll say goodbye. Bye then.
Alrighty. Thanks again.